Hello everyone, and welcome to Rowenga Surface, the implementation of aperiodicity into architectural acoustics. My name is Ross J. Cox, and I'm a research assistant at the Robotics and Digital Fabrication Lab at the John H. Daniels Faculty of Architecture at the University of Toronto in Canada. This project was done in collaboration and under the supervision of Research Associate John Nugent and Dr. Brady Peters. At the intersection of order and disorder exists a balance that is referred to as aperiodicity. It is this balance that we look to introduce to you and share some possible applications of it within design. An example of this mathematical concept that may be recognizable is the famous 2D Penrose tiling methods, which display local five-fold symmetries that quickly dissipate globally. Architectural designers have previously exploited properties of the Penrose tilings through floor tilings, sculptures, and building facades as seen here. However, like mathematicians and physicists in the later half of the 20th century, such as Nicolas Gauvert-de Broglie, Marjorie Senecal, and Paul Steinhardt, designers in the 21st century are now looking to the third dimension. Before we proceed further, a brief background overview is necessary to understand aperiodicity and its proposed application. In 1966, Wang's conjecture was falsified, meaning that it was proven that periodicity was not a requisite for tiling a plane. This led to mathematicians to subsequently discover several sets of tiles that were able to tile the plane in a manner that did not exhibit translational symmetry, forcing mathematicians to define a new class of tessellations. One of these new classes was aperiodic tilings. For the purpose of this talk, we will define an aperiodic tiling as one which does not exhibit periodicity. However, it is important to note that aperiodicity can have alternative meanings within other mathematical contexts. So these newly defined tilings, however, had excessive cardinalities attached to them, making them no more than a mathematical idiosyncrasy. In 1974, Roger Penrose, the future Nobel laureate, also found a set of 6, which he then eventually reduced to 2. What separated Penrose's work was the simplicity of his shapes, the local orderliness of the symmetry, and the aesthetic qualities that accompanied each tile. Because of these properties, Penrose's 3 tilings soon became the poster children for aperiodic tilings. However, while the Penrose tilings were fascinating and aesthetically pleasing set of mathematical objects, they lacked an algebraic structure, though in retirement, N.G. de Broglie saw an opportunity to rectify the situation. In 1981, he wrote a seminal paper on the algebraic theory and construction of Penrose tilings, in which he showed that they can be obtained from a mathematical construction known as a pentagrid. He also showed that this pentagrid was logically equivalent to a projection of 5-dimensional space, meaning that the Penrose tiling could be viewed as a 2-dimensional projection of 5-dimensional space. It was during his studies that an observation was made by his colleague, R.M.A. Rowenga, which came to light. Rowenga saw that the Penrose rhombi needed not to stay on the plane, but rather could be raised into the third dimension by an indexing method derived from an intermediate step in the projection process of 5-dimensional space. De Broglie named this surface a Rowenga roof, as he thought it could be used in architectural settings, particularly ceilings. Throughout this research, we noticed an interest by mathematicians and designers to develop digital platforms and software packages to create Penrose tilings. Some of these platforms even use the cut and project method for obtaining the tiling. The cut and project method is a well-established mathematical technique for harnessing higher dimensional space, such as this 2-dimensional lattice, and capturing it in a cutting window, in this case, a rectangular strip, and projecting the intersecting lattice points onto a lower dimensional space, in this case, a line. This method was alluded to in de Broglie's original paper. However, we found that it was very difficult to come across any platform that replicated the 3-dimensional analog of a Penrose tiling. We also found it hard to find any platform that constructed de Broglie's Rowenga roof. Due to these circumstances, we could not find a parametric script that allowed for the construction of a Rowenga roof. In this regard, we applied mathematics developed in the later half of the 20th century and developed a parametric script for the Rowenga roof, which allowed us to make a more generalized class of surfaces, which we have dubbed Rohingya surfaces. Here is a visual demonstration of the parametric script developed to construct not only a Rohingya roof, but also the variety of Rohingya surfaces. And here's a visual demonstration of the cut and project method from our script. A key objective of this research is to produce an open source work that could be shared with the design and mathematical community. While the construction of a parametric script for these Rohingya surfaces is novel, we found it pertinent to find an application for them. In recent years, there has been many experiments around acoustics and the Penrose tilings, including work at TU Delft. Additionally, in 2018, attempts to use the morphology of the Rohingya roof in acoustics in a similar manner to that of Schroeder diffusers was proposed by Rima Aliani. From our investigations into the mathematical properties of both Penrose tilings and the Rohingya roof, we have deduced that the needed rigor comes from the field of theoretical crystallography. Particularly in the field of crystallography, there was a discourse that had entrenched itself within the academic community that dictated that tessellations of unit crystal cells were thought to only be periodic due to observed physical properties and experimental results. This imposed periodicity on structure meant that a crystal needed to be spatially arranged to follow the crystallographic restriction theorem. Theoretical crystallographer Alan McKay looked to see beyond the restriction and postulated that the five-fold symmetry found within Penrose tilings could have a crystallographic cousin. He would first have to show that it could display a clear diffraction pattern, as this was one of the defining characteristics of a crystal. Therefore, using the vertices of the Penrose rhombus tiling P3, McKay generated a sphere packing of both the plane and space and put them through a mathematical transformation known as the Fourier transform. McKay's findings showed a clear diffraction pattern with strong and weak modulations of the transform as displayed here. In other words, there was clearly defined tenfold symmetry diffraction pattern after the transform was performed, indicating that there is an ordering within the aperiodic arrangement despite the lack of translational symmetry. This construction allowed McKay to theorize that arrangements of unit crystal cells could be both periodic and aperiodic. However, it was the clear diffraction pattern that allowed us to have the confidence in a potential for acoustic application for the Rohingya roof, something which had not been surmised before. This research, therefore, proposes combining the concept of aperiodicity with the predictability of a mathematical formula, and defined through a parametric model, where the acoustic performance of these aperiodic surfaces will be analyzed through simulations in an effort to build upon previous acoustic hypotheses. We looked at constructing a variety of Rohingya surfaces for acoustic simulation and used the Schroeder diffusers as a control variable. We used the software AFMG Reflex, which uses the boundary element method for calculating an acoustic simulation in 2 dimensions. Results showed a generalized comparability within the Schroeder diffuser in terms of scattering and diffusion properties. These positive results led us to begin to test various fabrication methods and surmise all of our findings in this paper. Like all research endeavors, these investigations are ongoing. 3-dimensional acoustic simulations are underway, as well as physical tests are being performed on individual test pieces. My most recent research project has been a 1-to-1 scale permanent Rohingya surface at the Fields Institute at the University of Toronto. Besides a research into fabrication techniques to construct these surfaces and an aesthetic addition to the Fields Institute's main lecture room, this project looked to physically test the acoustics of a Rohingya surface in an actual architectural space. T20, T30, and ED testing were conducted, and as per chart seen, we see a significant decrease in reverb time in the 2K to 8K frequency range. More in-depth information will be published down the road on this project. We would like to thank you for your time.